Everyone, does that make sense? And then what about the last piece here? 0. Okay, so now this is the partial derivative of f with respect to x, but we wanted to know the value of it at 2, 1. So the partial derivative of f with respect to x at the point 2, 1 will be replace the x with 2 and the y with 1. So you should get 2 plus 2 times 2 times 1 to the 5th, which is 6. All right. So what this means again is that if I were to plug in 2, 1 into the function, so I go out 2, I move over 1, plug that into the function, I'm somewhere on the surface. I'm going to be pointing parallel to the x-axis, and I'm going to take a step. And what's going to happen when I take that step? I'm going to be going up. My rate of change, my slope, is going to be 6. Rise over run. Okay? At that instant, that's what's happening. Now let's try this for the partial of f with respect to y. So we're going to do the partial of f with respect to y at the same point. So first the partial. So what is the derivative of y cubed? 3y squared, because now y is the variable and x is the constant. So this is now 3y squared. And then what is the derivative of 2x? 0, because it's a constant. The derivative of x squared y to the 5th. 5y to the 4th. So you're just doing power rule on this, and then the x squared just coming for the ride. So I'm going to write it. I thought it was plugged in. Oh, did I unplug it? I unplugged it when I walked out. Everyone's like, please let it die. Let it die. Let it die. I never plugged it in. You know, last time it told me I had like 42 minutes remaining. It died like 2 minutes later.
I know. That's what I'm praying for. I'm sorry. It's not you. It's just...
No, I know it's not me. It's you. You signed up for it. It's a long class, man. It's brutal. But hey, what else would you rather be doing, you know, than calculus 3 in the summer? I mean, what else? I can't think of much better things to do. All right, so that's that. And then, okay, so we said this was going to be 5x squared y to the 4th, and there's nothing else, right? That takes care of everything. And now we need to plug in 2, 1. So this is 3 plus 20, right? 3 plus 20? So 23. Yes? I'm going to do a visual again for you. I know you get it. Maybe you get it. Maybe you don't. But check this out. I'll go out 2, move over 1, plug that into the function. I'm standing up on this surface, right? If I take a step in that direction, I have a slope of 6, right? Pretty steep. But if I take a step in that direction, I have a slope of what? 23. Really steep, right? So that direction that way, this direction that way. Like that, right? Do you think there's some way later on that we might be able to just look at these as vectors and actually come up with the equation of the plane through that point? And wouldn't that plane then, in some respect, be tangent to that surface? Does that make sense? We'll do that later, but I'm trying to get you to see these partials mean more than just a number. They're giving you some rates of change. So if I'm standing at this point and I want to go up really fast, I should go that way, not this way, right? Yes. And then there is an ultimate question, which is which way do I point? If I'm allowed to go in any direction, which way should I point to get the steepest? Or is 23 the steepest? Does that make sense? Yes. So we'll be able to do that. It's not yet. Yeah. Okay, take a few minutes to try and take the partial derivatives of that. We'll see how you do with that. What sorts of rules do you think you're going to need to incorporate if you're going to take those partials? You're going to have some chain rule because it's sign of something, right? And then inside there, what kind of rules do you think you're going to need? Quotient rule? You got a little quotient rule in there? And maybe some product. Well, would that be a product though? Because if you're holding one of them constant, you'll never have to worry about a product rule there, right?
Yeah, you're right.
Okay. So all right, take a few minutes to see if you can crank out that partial derivative. Look, these are the things that you have to be able to do the mechanics here to do anything else. Like these are the, yeah, like if you struggle with partial derivatives, then everything else later becomes impossible. So make sure you can do this. Miller time. Can I get in trouble for that? It's 2019. I'm off camera opening something and saying Miller time. Can I get in trouble for this? I thought of taking my Crown Royal bag off my camera. I know you don't care, but you know, some people do. All right, crank it out, see what you get. If you need help, just raise your hand, or if you want me to check what you've got, I can come by and take a look. If that sunlight bothers you at all ever, you can close that, man. Because that would bother me. You want to close it? Yeah, close it, man. You're like cooking over there. Unless it's broken. No, yeah. Has that been bothering you the last couple of days in here? You're all like got sunburn on your neck and stuff?
Yes, that's it. And the derivative inside is going to be a quotient. Well, the top is going to be. It's going to be relatively high minus high. Is x squared. Yeah, so it just becomes cosine x y over squared y. But you don't get rid of it. You don't get rid of it. Yeah. Not the first one. No. The second one you do with that point it's okay, so part one cosine and then everything equals the same. Yes. Okay, all right. Part one. Figure making one constant would make
So x squared y minus 2x squared y.
Wait, isn't that the same? So
are you talking to me or no?
no, never mind. I'm not talking anymore. I'm good.
All I hear is wait, though, and I don't know if you're talking to me or not.
It's fine.
So I'm here to help you, learn this stuff, right? So if you have a question about how I'm doing any of this, just, now is a good time to ask if there's any confusion as to what I am doing. Now, I only did one of them. I haven't done the other. They're very similar answers.
Yeah, wouldn't the other one be?
This part would be the same,
Yeah,
right?
that part would obviously be the same.
Yeah. And then this right here would be an x instead of a y.
Correct.
And over here that would be 2y instead of a 2x.
Yes.
Otherwise, it's the same.
Yes. And as a result, because of that, you would end up having.
You good?
Yeah.
You okay with that? We're all good over here? Yeah, unfortunately. Yeah. So this is a little chain rule, right? Start out, taking derivative of sine of something. Anytime we have that, we have to just rewrite it cosine of that something. Then we multiply times the derivative of what's inside, which means we do a little bit of quotient rule, and I heard some Lodi high or something like that, or whatever you learned. However you learned it, we're going to be taking the derivative of the top one, right, with respect to x, which means y is a constant, right? So it's just going to come for the right. Derivative of x is 1. 1 times y is just y. So that's this, then times the bottom, and then minus, because that's what quotient rule says to do, the derivative of the bottom with respect to x. 2x plus 0. So 2x, and then times the top one, and then over the bottom one squared, and then you can clean it up from there, but that's the basic mechanics there. Okay? Let's proceed. So there are lots of different notations for partial derivatives. Bunch of different ways you might see this presented to you in a textbook or in this book. And these different notations come from the idea that the calculus was developed by two people. There were two separate people who actually came up with calculus, Newton and Leibniz. And amazingly, they kind of did it at the same time, like at the same period of time. They both were doing it and independent of one another. So they didn't know the other person was doing. So they were creating mathematics on their own. And so one of them created their own notation, and the other one used their own notation. So that's why we have kind of this is our Leibniz notation, and then our Newton notation is more of the primes and the subscripts. But it all turns out that sometimes this notation is nicer to work with, and sometimes this is better. So if you have a surface, okay, f of x, y equals z, if you've got this standard surface, function of two variables, all of these mean the same thing. So the following are equivalent. This is the notation I started with, but if you just see the x there, like I showed you already, then that means the partial of f with respect to x. This is like dy dx, but we use this partial symbol. I've heard different names for it. Del is one I've heard, but del can be something else. So it's kind of a curvy d. So this is like your standard d. This is like that's your partial. So it's your partial of f with respect to x, partial of z with respect to x, the partial with respect to x of the function, or f1. I like this one, f1. This means you're taking the derivative of f with respect to the first variable, right? So x, y, so the first variable. This is useful if you have maybe 30 variables, because then you run out of letters, don't you? So maybe you have a function of 30 variables and you want to take the derivative of the 29th variable with respect to the 29th variable. So nice. This is like d, take the derivative, right? Take the derivative of this function with respect to the first variable. This one, they go back and they say, forget the first, then we'll just go back to x. Take the derivative of f with respect to x. So these all mean the same thing. And just like we had in calculus, there are higher order derivatives. So if we can take the first derivative, we can take a second derivative, and a third and a fourth. But there's a big difference, because if we were in Cal 1, we take the first derivative, second derivative, third derivative. Every time we do it, the variable is always x, right? But here, I can do a first derivative of a function with respect to x, and then that second derivative, I can do it with respect to y. And maybe I decide to then follow that by doing it with respect to x. So the order that you do these matters. So we have a notation for it. So right here, these are just the second order partial derivatives. So the notation f subscript x in parentheses with another x means you're doing the derivative with respect to x twice, or 1, not 11, with respect to the first variable twice, or with respect to f, partial with respect to, partial of f with respect to x, do that, then take the partial with respect to x again. Or you could put squared here, squared here. Anyone know why those squares are offset? Why they offset the 2's? Is that just to make the notation look even crazier for you?
No, it's because the multiplication thing, the previous step, because we have the symbol and the symbol times the symbol of f. The symbol is actually being multiplied together, so f is still just one side.
Yes, you have df dx and multiplied by d dx.
Oh, like this?
Yeah.
I guess you could perceive it that way. Like you're doing this and this, so that one's squared? Is that what you're saying? Is that what you're saying? Okay. Well, let me explain why I think they do it, okay? Because if I did this, what might you think that means? You might think this means that you're taking the derivative of f with respect to x and squaring that answer. So by offsetting the 2's, there's no confusion. You read this and you understand you want to take the partial twice instead of partial squared. All right. This pretty much the same thing, right? This is the one I think is the one you have to pay most attention to. Because the order here matters. The order matters. So if you see x followed by y, if you're reading this like a book left to right, x followed by y, which partial are you doing first? The x. So you read it from left to right like a book. All right? Same with this one. This one, yx, you're going to do the partial with respect to y first, then take that answer, partial with respect to x. I'm sure you're curious as, what do these mean? Like, what are these second partials useful for? It's coming. Let's see what my next one is. What are we doing on time? Yeah, that's a major theorem right there. Let's only do one of these. There are four second partials for this, right? There's fxx, fyy, fxy, fyx. So let's do one of them. How about fyx? So I'm going to first differentiate with respect to y, right? So let me do that separately. Let me do the partial of f with respect to y right here. What's that going to be?
That's going to be
20y what? To the fourth minus? So 10x cubed is a constant. So you're taking derivative of y squared. So the 20 what? X cubed y. Okay. Now let's take the partial of that with respect to x. Sorry, I didn't mean to do that. So the partial of... So this is going to be the partial of that with respect to x, which is just...
It's just going to be...
So y you ignore, negative 60 x squared y. All right. So the derivative of that's 0 if you're differentiating with respect to x. And then this one, you ignore the y and the negative 20. You take derivative of x cubed. That's 3x squared. And then tack these on. You know what? I changed my mind. Let's do partial of f with respect to x, then y. Let's do this one.
Okay.
Do you think we get the same answer?
No.
Let's see. So what is the partial of f? We're going to go with respect to x first, right? So with respect to x, we get 2x minus 30 x squared y squared.
Oh dear.
Oh no. Do you see it? Let's take the partial of that now with respect to y. And what do you have? The same thing. Look, so you're doing now with respect to y of this, so that's gone. And then here, that you cover up, derivative of y squared is 2y. It comes out and makes our negative 60 x squared y. Coincidence or always true? What do you think? Always true?
I thought order mattered.
The order does matter in the notation, okay? Because we can have third derivative now. We could have like, in theory, you could have like fx y x y y. Like that would mean you need to do y first, then y, then x, then y, then x, then x. Now, if there's only two, right, does the order matter? We're about to find out. The theorem is going to tell us, all right? It appears right now that for at least this example, the order didn't matter. At least for this example. All right, Klotz theorem. Given some function of two variables, if f is defined on a disk D that contains the point x naught, y naught. So this is mathy stuff right here. This is just saying, hey, look, you're standing on this surface, okay? You're sitting there at this point. You know, you went out x, you went out y. That's x naught, y naught. You went out x naught, y naught. You're up here on this surface. As long as your function is defined, your surface is defined on some disk around you. Like, what we need is that if I take a step to the left or to the right or back or any direction, that I don't just like fall off the universe, like there's not a hole there. So as long as I've got some little patch that I can stand on, and the partials are both continuous, that means that when I take these two partials, which I have them, these second order partials, as long as these guys are defined, I don't get division by zero or any sort of weird crazy crap happening within that little patch, they're always the same. So it's all going to depend on the function, but the conditions are not that strong. We just need to have a defined function in that little neighborhood, and we need to have that the second partials don't go haywire and crazy in that little neighborhood. Otherwise, they should be the same. All right? Now, we're not going to prove the theorem, but we will take it, and we're going to use this later. It's going to be an important thing later. I should prove Klotz's theorem one of these days because it's so important later. It'd be nice to know why that's true. I think that's a good time to end the class right there. I think you get the idea what you need to do here, right? Hit it with the, x. Wait, when I did that earlier, I did y, didn't I? I did that backwards, didn't I? Let me restate. This one would be x, y, x, y. Sorry. This one, x, y, x. This one would be y, x. All right, we'll pick up with that next class. A little bit about Laplace equations. Implicit differentiation. All right. Have a great weekend, everyone.